Today, we are going to do some notes on the Bohr model and the electromagnetic spectrum. So if you remember Bohr, we discussed his model back in Unit 3 when we talked about our different scientists. And what was unique about the Bohr model was that he said that electrons orbit the nucleus in circular fixed paths of energy that we call energy levels. Sometimes you might have referred to these as electron shells, and that works as well. And what Bohr's model helps us do is explain how we can see light. So, how the Bohr model works is even though they are in these circular paths of fixed energy, electrons can jump from energy level to energy level. And the energy levels are kind of like the rungs of a ladder, but they are not necessarily equally spaced. So there's two different states we're going to refer to. We're going to refer to the ground and the excited state. And the ground state is the lowest possible energy level that an electron can be in. And the excited state is any energy level that's higher than the ground state. So electrons can go from the ground state to the excited state, but in order to do so, they must absorb energy. And they can do this in either the form of heat or electricity. And then the electrons, once they go to that excited state, they don't stay there forever. In fact, they quickly move from the excited state back down to the ground state. And when this happens, that is when photons are emitted, and we see this in the form of light. And a really fancy scientific way to say light is by calling it the electromagnetic radiation. So electromagnetic radiation is just another scientific word for light. So if we look at this Bohr model right here, let's go through this process. So first, we have an electron that is in the ground state. So right here, we're in the ground state. And we could call that the first, or actually in this case, it's at the second energy level. Then what happens is somehow this electron can absorb energy. And it absorbs energy in the form of heat or electricity, and it jumps then to this excited state. However, it can't hold on to that energy. So what happens is it then falls back down from the excited state, which we should label here. So it falls back down to the ground state again. And when it falls down to the ground state, this is when it emits energy in the form of a photon. And a photon is light, which we can sometimes see. Now, this light that gets emitted produces something called an emission spectrum. And depending on what substance the electron is in, it's going to produce a different emission spectrum because the emission spectrum is unique for every single element, just like a fingerprint is for a human. Now, Bohr discovered all of this while he was studying the element hydrogen. So this is the Bohr model for the element hydrogen. And these are all the different ways that an electron can jump. So, for instance, sometimes that electron jumps up to the third energy level, and when it falls back down to the ground state, it produces a red light. Sometimes it jumps to the fourth energy level, and when it falls back down to the ground state, it produces blue green. Sometimes it jumps and it produces violet. And then you can see here, if we were looking at the emission spectrum, this is what it would look like for hydrogen. And we will actually get to see some of these emission spectrums here a little bit later on, not in our notes today, but in a lab or in a video. So that's the Bohr model, and it explains why we can see light. Going back up to this, that photons are emitted in the form of light called electromagnetic radiation. We have lots of different forms of light that we can see. And all the different forms of light are called the electromagnetic spectrum. So the electromagnetic spectrum contains all of the frequencies and all of the wavelengths of the electromagnetic radiation. So it's all of our light. Frequency is sometimes shown with the Greek letter nu. It looks a lot like a V, but that's the Greek letter nu. And wavelength can be shown with the Greek letter lambda, which just looks like an upside down Y. So if we take a look at the electromagnetic spectrum, here we have this figure. You do not have to memorize this figure. It will always be given to you. And over on the left side of the electromagnetic spectrum, this is where we have our highest frequency and our shortest wavelength. It's also where we have our highest energy. On the right side is where we have our shortest frequency, our longest wavelength, and our lowest energy. So a lot of times when you hear the word radiation, you always think that it's something bad, but it's actually not something bad in many cases because a lot of light has such low energy that it can't really cause harm to you. So, for example, one type of wave that will not cause harm are radio waves. So we can see radio waves right here on our electromagnetic spectrum. And radio waves have a very long wavelength and a short frequency. And they don't have enough energy to hurt you, right? You won't be harmed by listening to the radio. The next type of wave that we should look at are microwaves. So this is what you use in your microwave in order to heat your food. Once again, not going to cause you harm. And then we keep getting a little bit higher frequency, a little bit higher energy, a little bit shorter wavelength when we get to infrared light. And then really the part where we care about the most, because we can see this, is something called the visible spectrum. So these are light waves that we can see the frequency with our eyes. And if you look, you can see that we have a rainbow here. So we have Roy, red, orange, yellow, green, blue, indigo, violet. So the visible spectrum, how we think of it as Roy G. Biv, is actually in order from the longest to the shortest wavelength, or from the shortest frequency to the highest frequency. So the highest energy light, remember, is going to be on the left. That would be violet. And our lowest energy light would be red. After the visible spectrum, we now get into types of waves that actually might cause us some harm. For example, up next is UV light. So, UV light, a good source of that is from the sun. As you know, when you go out in the sun, you need to wear sunscreen because otherwise, the sunlight does have enough energy that over time it might mutate your DNA and cause problems in your DNA and cause you to get cancer. So, UV light would be one of our more harmful types of radiation. Even more harmful than UV would be X rays. You can go out in the sun every day of your life and never develop skin cancer. However, X rays, they have a limit of how many X rays you can have in a certain time period because X rays have even more energy than do UV light rays. So, X rays are more harmful. And then our most harmful on our electromagnetic spectrum would be gamma rays. And these are things that they use in things like CAT scans and CT scans, which is why you can get those even less frequently than you get an X ray. So, on the electromagnetic spectrum, you can see that there are really only three types of radiation that something might emit that would cause you harm. And there's a whole lot of types of radiation that wouldn't cause any harm. So, the word radiation does not always mean something harmful. What we need to be able to do with our electromagnetic spectrum, though, is relate these things. So, something important to keep in mind that all waves on the electromagnetic spectrum are light waves, which is really weird to think about radio waves are light waves, but they are. And why this is hard for us to grasp is because we actually can't see most of the electromagnetic spectrum. We can only see that small part, which is the visible spectrum of light, which is what we have highlighted right here in our notes. And as humans, we can really only see a very small portion. And this portion has the wavelengths from about 400 to 700 nanometers. As we said above, the waves on the left are what have the most energy, while the waves on the right have the least amount of energy. And you do not, I repeat, you do not have to memorize the spectrum, but you need to be able to explain certain relationships such as wavelength, frequency, and energy, like we did above. And we'll have some practice questions below. So, an equation that you don't have to memorize and we actually aren't even going to use, but I just want you to be aware that exists, is the equation C equals lambda nu, where C is the speed of light, lambda is wavelength, and nu is our frequency. And the speed of light is something that's going to be constant through a vacuum. And so this C is not going to change. So think about it mathematically. If my wavelength is increasing and my C is constant, in order for C to stay constant, my frequency must decrease. Which makes sense from our graphic above, right? Where we had our shortest wavelength, we had our highest frequency. Where we had our longest wavelength, we had our shortest frequency. The next equation that you, once again, aren't going to have to use, but we want to be aware that it exists, is that energy equals H nu. So E, as I said, is energy. H is something called Planck's constant. And Planck's constant value is not important, 6.626 times 10 to the negative 34th. What is important is that it is constant, just like our speed of light. And nu, again, is frequency. And what this equation allows us to do is relate energy and frequency. So as energy increases, our frequency also increases. So notice these two equations that I outlined below. We can see all of those relationships already on our electromagnetic spectrum above. Our highest frequency is going to be our shortest wavelength. Our highest frequency is also going to be our highest energy. Our shortest frequency is our lowest energy. Our shortest frequency is our longest wavelength. But for those of you who are mathematically inclined, these equations really help you see that. So what type of question might you be asked? Well, here I have that electromagnetic spectrum again, just so that we can see it to answer these questions. And our first question is, what color of light would have a higher frequency than green? So if we look, here's our visible spectrum, here is green, and it wants to know which one has a higher frequency. So if we remember, our highest frequency is going to be on the left. So we want something that's going to have a higher frequency than green. Well, red would be to our right, so not red. Yellow, also to our right, so not there. Blue, that's to the left, that is higher, so possibly blue. And orange, nope, that's also to our right. So our answer here would be blue, would have a higher frequency than green. Another question, which of the following are waves with the highest energy? So highest energy, remember, are going to be the things to the left. Lowest energy are things on the right. So we want to see what is the furthest to the left. So we have X-rays, UV, yellow light, and AM radio. So AM radio, no. Yellow light is here. UV and X-rays. So which one of those have the highest energy? That would be our X-rays. And last but not least, which waves would have a wavelength longer than red light? So if we look here, if I just erase my previous, we want red, and we want something that has a longer wavelength. Remember, over here are going to be our longest wavelength. Over here are going to be our shortest wavelength. So we want something longer than red. Our choice is blue light. No. UV light. No. Microwaves, possible. And both A and B. Well, we ruled out A and B, so our only ones that would be longer here are microwaves because they're to the right of our red light. So just be prepared to using a diagram, because once again, you don't need to memorize the electromagnetic spectrum, be able to answer multiple choice questions such as that, and you should be just fine. All right, thank you.